Continue. Basically, as I said, this is the definition of a mathematical model. So it's a set of mathematical relations which correspond to physical or logical relationships in a real life problem. Okay. So what kind of examples actually can be modeled as a mathematical model? Well, for instance, if I go back to the example of portfolio optimization, so if I have 10,000 Turkish liras right now, then I cannot invest more than 10,000 Turkish liras, right? So this would be, again, an example of a relation that can be modeled as a mathematical relation, right? So if I have a variable that corresponds to the amount of investment, then the amount of investment cannot be more than what I have, okay? So again, we would end up with an inequality, of course, in this time with less than or equal to type of relationships, right? So if x is the amount that I'm going to invest, x cannot be larger than 10,000, or x should be less than or equal to 10,000, okay? And I also talked about logical relationships. So basically, if I go back to this example, a plus b is equal to 10, or more precisely, 2 times a plus b is equal to 20, is the mathematical relation that defines the fact that the amount of wood you can use, the length of wood you can use, should be exactly 20 meters, okay? So we take this verbal description and turn it into a mathematical relation, which corresponds to this verbal description. Is that clear? Okay. All right. So as a result, we started with industrial engineering. Then we talked about operations research. Then we talked about optimization. Then we talked about mathematical model. So as a result, an optimization problem is something that arises from a real-life problem, such as this one, but can be modeled using a mathematical model. And then in this course, we're going to first see how we can model different problems in this form. Then we're going to talk about how we can solve these problems. Okay, so far we haven't seen how we can solve this problem yet. Of course, you know how to solve this problem, but we haven't seen how to find values of a and b systematically so that a times b will be as large as possible. So this is going to be the second part of the course. Okay, so as a result, in the first part, we're going to only be dealing with the modeling aspect. Okay, we're going to try to construct a mathematical model that corresponds to a real-life problem. And in the second part, we're going to actually try to solve this model. Okay, we're going to try to find the best value of a and b, and then we're going to take that solution and turn it into the context of the original problem. So if a is equal to 5 and b is equal to 5, then I'm going to go to the person that gave me this problem and say that, well, you should actually build a fence which is 5 by 5. Okay? So as I mentioned, the first part is modeling. The second part is solution of this model. Okay? All right, so let me briefly talk about the history of operations research. Now, if you think about the word operations research, it sounds kind of strange, right? So what kind of operations are we talking about? Okay? And why is it called operations research in the first place? Why not something else? Well, there's a reason for that, because actually the word operations comes from military operations. Okay? And essentially, OR has been around for about 50 years or so, 60 years, let's say, more precisely. And it actually picked up, it started to gain importance during the Second World War. Okay? Now, during the Second World War, of course, as you know, the British Army was sort of fighting with the Germans and so on and so forth. And they had some casualties, okay? So they had some losses, for example. They lost some battleships, they lost some troops and so on and so forth. And what they wanted to do was they wanted to use their resources more effectively, more efficiently, okay? And this is actually when this all started, okay? So how should we, for example, move our submarines so that they're not going to be attacked, or they cannot be attacked? Where should I drop the bomb so that I can actually make the largest damage, okay? Now, if you think about these problems, all of these actually have some sort of optimization built in it, okay? Well, it's not a very nice form of optimization, but still, you want to make the most effective bomb. You want to make the sort of the strongest tank or something like that, okay? So this is when it all started. So during World War II, the Second World War, so a team of scientists studied the strategic and tactical problems and technical problems associated with air and land defense. Air and land defense of England. So they start actually with these problems, which of course at the time was one of the most important problems. And then they started to get some encouraging results. So they took these problems, and just like we did, they actually modeled it as an optimization problem. And then they tried to solve these resulting models, okay, the models that arise from these problems. And it turned out that the decisions based on these models turned out to be effective. Okay, so they indeed actually decreased their losses. They started to gain power, and so on and so forth. So as a result of which, essentially, people realize that this is something worth studying, right? This is something worth looking into. Okay. So let me say that encouraging results motivated U.S. military management to start similar activities. So once again, it started with the British, basically. And then the US military officials realized that, well, we should maybe do the same thing as well, and they started doing that. And now soon afterwards, after the World War was over, so they said that, well, this actually can be applied to other settings as well. Okay, so this can be applied to settings like, manufacturing, facility location, and this and that, and so on and so forth. And then, OR actually found a lot more applications later on. Okay, but the reason why it's called operations research is indeed because it comes from military operations. So that's the root of operations research. Okay, so the word operations indeed actually referred to military operations in the first place. Okay, but then they didn't change the name, so we still use operations research. But this is the reason why it's called operations research. Okay, so finally, similar models can be employed for various other areas of industry. For example, one problem that they looked into was the following. So suppose that you have a communication network. Think of like the phone system, right? And what you want to do is you want to somehow destroy the communication system of your enemy. Okay? And the question is, for example, which facilities should you bomb to make sure that they're going to be disconnected from one another? Okay? And of course, you want to do this by damaging the smallest number of facilities because you don't want to use, too much of your resource and so on and so forth. So what's the smallest number of stations that I should hit so that they're not going to be able to communicate with one another? Okay? And as you know, communication is important during a war. So this was one of the problems that they looked into. Okay? Or how should I, for example, lay out my submarine so that I can minimize the potential sort of enemy threat? Okay? If your submarines are too close to one another, then a single bomb can actually destroy both of them. Okay? So you have to make sure that they're spaced out equally, but at the same time, they should be too far away from one another because if there's a problem, then the other one should be able to help quickly. Okay? So if you think about this a little bit, this kind of trade-offs, that's what we call them, they're everywhere basically. Okay? So if I go back to the call center example, so if you hire too many people, then you're going to pay too much money, but the customer will be happy, right? No one will wait. Well, if you hire too few people, then you're not going to be paying too much money, but then the customer will be unhappy, and they can actually choose a different cell phone service. Okay? So there are similar trade-offs everywhere in different applications, and your goal is to sort of balance the two. Okay? And this is precisely what optimization is all about. So basically, you have different sort of goals. You want to sort of make the best mix of decisions in some sense. Okay? Any questions? All right. So there's one last thing that I would like to talk about before we really start the course. So the bottom line is the following. OR is a decision-making tool. So this is important to keep in mind. So this is a tool that we use to make decisions, to make good decisions, okay? Not arbitrary decisions, but to make good decisions. And what defines good? Well, what defines good depends on the problem, okay? In the fence example, good decision is the one that gives you a large area, okay? In the call center problem, well, the good decision is one that actually gives you a trade-off between the customer satisfaction and the amount of money that you spent, okay? So usually there's the following diagram that you should keep in mind. So we start with a problem. And this problem actually can come from quite different settings, okay? It can come from a military setting, it can come from this like call center problem. It can come from such a setting as well. So usually we start with a problem, okay? And then what we do is we take this problem and we actually build a model of it. Just like we did for this example, okay? So we decide about our decision variables, the variables that we can control. We look at the limitations, which are beyond our control. Then we try to sort of come up with certain equations, certain relations that should be satisfied by decision variables. And this is known as the modeling process. Okay? Then once we have a model, then we analyze the model. Okay? And when I say analyze, I also talk about actually solving the problem, solving the model, and also using that to maybe strengthen the model and so on and so forth. And we make some conclusions. Okay? Now, based on these conclusions, we actually make certain inferences about the problem. So inference basically means you deduce something, you conclude something, okay? Then we actually make decisions based on that. For instance, if I go back to this example again, so the best values of A and B are equal to 5. So I take that, and then I give it to the person who gave me this problem, and I say that, you should use 5 by 5, okay? So I take the solution from my model and turn it into the setting of the original problem. Okay? And then we need one more step to actually close the loop. Then we assess our decisions. So what does that mean? So, we take the solution from our model, and then we see whether actually those decisions are valid in some sense. Okay? And why do we need this? Well, because essentially, in real-life problems, the problem is, most problems are quite complicated. Okay? So as a result, there might be a certain aspect of the problem that you haven't sort of thought about or you haven't considered yet. And the decision may tell you that, your decision does not satisfy certain requirements. Okay? So for instance, if I go back to the example of course registration, you come up with a curriculum, you come up with a bunch of courses. You actually construct a model. You want to, for example, come up with a curriculum so that all your classes are in the afternoon. Okay? And then, you look at your solution from the model. Well, the solution tells you to take IE-303, for instance. Well, you cannot do that, right? Because you didn't take IE-202. Then you go back to your model again, and you actually put that as a constraint as well, as a limitation as well. Okay? You say that, look, among the decisions I make, I cannot really take IE-303. So you have to do something about that. So what do? Well, I update my model, I solve it again, and this time I get a different set of decisions. Okay? And usually we go actually through this loop several times. Okay? In real life problems, we start with the problem, we model it, we make conclusions, we look at decisions, we assess decisions, then we revise our model and so on and so forth. Okay? So usually, as I said, we go through this loop several times, and you're going to do this same thing actually in your senior design project as well. Okay? You're going to start with a problem, you're going to model it, you're going to make conclusions, and you're going to make decisions. Okay? So it's a good idea to actually keep this loop in mind. Okay? Questions? All right, so now we're going to really start the course. So I'm going to start with basic examples. Okay? So essentially, in this part of the course, which will be about 6 weeks or so, we're going to look at how we can model the problem. Okay, so you give me a real-life problem. How can I construct a mathematical model of my problem? Okay, so that's going to be our focus in the first 6 weeks or so. Before that, any questions again? So, all right. So here's an example. So suppose that there are two machines. Needed to process milk. Okay, so suppose that you actually produce milk, and in order to produce milk, you actually need two machines. And you process milk to produce, let's say, two kinds of milk. So let's say low fat and regular milk. Okay? So of course, I mean, low fat and regular milk should have different processes, right? Otherwise, the outcome would be the same. So suppose that here are the processing times. So the first machine is for pasteurization. So let's call this machine 1. And the second one is for homogenization. Okay, so let's call this machine 2. And then I'm going to give you the following table. So I have low-fat milk, and I have regular milk. So on the first machine, we can process 1 liter in 3 minutes. Okay? So for 1 liter of low-fat milk, we need 3 minutes on this machine. Okay? And on the second one, we need 1 minute to process 1 liter. Okay? For regular, we only need 2 minutes on the first machine per liter. And on the second one, we again need 2 minutes. Now, what does this notation mean? So to process 1 liter of milk, I need 3 minutes of the first machine. Okay, 3 minutes time on the first machine. And similarly, to process or to produce 1 liter of low-fat milk, I need 1 minute on the second machine. Okay? So as a result, in order to produce 1 liter of low-fat milk, I need 3 minutes on this machine plus 1 minute on the second machine. Okay? And similarly for the second one, for regular milk. Then we assume that the sales price of low-fat milk is, let's say, 2.5 liras per liter. And similarly, the sales price of regular milk is, let's say, 1.5 liras per liter. Okay? So each liter of low-fat milk I can sell for 2.5 liras, and each liter of regular milk I can sell for 1.5. Okay? We have another limitation. So in a day, machine 1 can be used for 12 hours. And machine 2 can be used for for 6 hours. So why do we have these limitations? Well, maybe, you know, there's a maintenance that we have to perform, okay? So, or maybe we're renting the machine from somebody else, and we have only that much time that we can use. And the question is the following. So how much regular and low-fat milk should be produced in a day to maximize total revenue? Okay? So essentially, I mean, this is like a production planning problem. Okay? We have only two products, low-fat milk and regular milk, and we have two machines to actually produce this. And what we want to do is we want to sort of figure out, we have limitations on the machine time that we can use in a single day. And what we want to do is we want to sort of figure out how much low-fat milk and regular milk we should produce so as to maximize the total revenue at the end of the day. Okay? So we're sort of thinking about a daily production schedule. Okay? Is the problem clear? So it's a simple problem. Okay? Of course, I mean, there are some restrictions, right? I cannot really produce an infinite amount of milk. Why not? Because I have limitations on my machine time, right? Okay? So ideally, the more I produce, the better off I am, because I assume that I can sell whatever I produce, okay? Under the assumption, of course, I need to produce an infinite amount of milk. Then I can make an infinite amount of money, but the problem is that there are certain limitations that I need to take care of, okay? So what we want to do is we want to start with this problem. This is a very simple problem, and we want to formulate it, or we want to construct a mathematical model for this problem, okay? So the first question we need to answer is the following. So what are the variables that we can control? What are the unknowns that we would like to determine and we don't know yet, but we can control? So what can we control in this problem?
Different types of milk we can produce.
Exactly. So there are basically two things I can control in this problem. And the first one is how much low-fat milk I'm going to produce. And the second one is how much regular milk I'm going to produce, right? So this is something I can control. This is something I can control, but there are certain limitations, right? So I'm not completely free, basically, to produce anything I want, okay? What are the limitations? Well, I need to make sure that I cannot use more time than the available machine time, okay? All right, so let's start with the first one. The first question is the following. So what are the unknowns that should be determined by the decision maker? Well, as we said, in this particular problem, there's actually only two variables, okay, or two unknowns. I'm going to call them x1 and x2, okay. So x1 denotes the number of liters of milk, low-fat milk produced in a day. So I'm going to denote that by x1. Okay, just like our A and B in the previous example. And by x2, I'm going to denote the number of liters of regular milk produced in a day. Okay? Now, essentially, so these are our decision variables. So these are the variables that we can control. Okay? All right, so let's move on. So at least now we know what the decision variables are. Now the second question is the following. So what are the ingredients that we cannot control in this problem? So what are the factors beyond our control that we have no control over? So here again, I'm assuming that the world is a deterministic place, okay? So there's no randomness involved. So I'm going to assume that my machines will not break down and so on and so forth. So what are the factors that I cannot control? Yes? Exactly, that's very good. So essentially, the available time on machines is something I cannot control, okay? So it's actually given to me. What else? That was good. Yes? The prices, exactly. So I cannot control the prices either. Okay, so they're also given to me. Okay, so these are not decision variables. Yes. Exactly, that's also good. So we cannot really change the products. Okay, so we're given that we have two products. So essentially, the available time on the machine is something I cannot control. The sales price is something I cannot control, and number of products is something I cannot control. Number and mix of products is something I cannot control. Okay. So unlike the decision variables, I have no control over these. Is that clear? Okay. So I'm going to assume that they're given to me, so I cannot do anything about them. Okay. So I need to live with those limitations, with those sort of factors. So that's the second question. So what are the technical factors which are not under the control of the decision maker? Well, as I said, available machine hours would be one of them. Okay? Yes? We also have limited number of machines. So number of machines is also something I cannot control. Okay? Like the number of machines. Then we cannot also control required machine hours actually per product. So what do I mean by that? So we cannot really change, for example, number of minutes per liter. Okay, that's also given to us. We cannot change the revenue per unit of each product. And we cannot change the number and mix of products. So I'm going to use this symbol over and over again. This basically means number, okay? So as I said, unlike the decision variables, these are factors we cannot control. So these are given to us and we have to live with them, okay? So to distinguish these from the variables, we actually call them parameters of the problem, okay? So these are the parameters of the problem which cannot be changed. Okay? Is the distinction clear between the two? So decision variables are some things things that we can control, and these are things that we cannot control. So we're given. So for example, if I go back to the example of, getting home as quickly as possible, you cannot really build new roads, right? So the roads are given to you. Okay? So you have to take them, and among those roads, you have to find the best one. Okay? All right. So the next one is, what are the physical limitations? So what do I mean by this? So what prevents us from producing an infinite amount of milk, for instance? Okay? Now ideally, the more I produce, the more I sell, right? By my assumption. So what I want to do is I want to produce as much as possible. But the problem is that I cannot do that really, right? So I cannot produce as much as possible because of the because of which factors? Time limitations on machines. That's very good. So let's write that down. So total production time on each machine cannot exceed the available machine hours. Okay? What else? Can I say something else about x1 and x2?
Non-negative.
Exactly, that's very good. So x1 and x2, they actually correspond to production amounts, right? So as a result, I cannot produce a negative amount. So x1 and x2 should be non-negative as well. So production amount should be non-negative. Okay? So we start with decision variables, then we continue with parameters. So what about these physical limitations? Well, they also have a special name, and we call them constraints. So these are the constraints we should obey. So we have to live with these constraints. Okay? Now, if you think about this a little bit, if I go back to the original example, the area problem, so remember we had three relationships, right? So 2 times a plus b is equal to 20, a is non-negative, and b is non-negative. And that defined the allowed set of values that we can use for our decision variables, okay? Now, more generally, actually, the constraints will determine the allowed sets of our decision variables, okay? So whenever I pick values for x1 and x2, I should make sure that I satisfy both of these restrictions, okay? So in other words, the constraints actually give me the values that I can choose for my decision variables. Okay? So once again, you have to keep in mind the fact that the constraints actually tell you the allowed values of x1 and x2. Okay? All right, so number 4. So the question is the following. So how do we compare two different solutions? So what do I mean by that? So for instance, suppose that somebody tells me that x1 should be 10 and x2 should be 0. Okay? And somebody else tells me that x1 should be 0 and x2 should be 10. Okay? So which one should I pick? So how would I know that if anyone is better than the other one?
If they're not passing the physical limitations, the one that generates more revenue.
Exactly. So essentially, I'm interested in maximizing my revenue, right? So as a result, if you give me two different solutions, then I can say that this one is better than this one if the total revenue from this one is larger than this one. Okay? So as a result, we actually compare the total revenue arising from each solution. And the larger is better, basically, right? So whichever gives me a larger total revenue is better. And we actually call this the objective function. So the objective function is the function that we would like to maximize or minimize. Okay? So in this case, we would like to maximize this function. In the previous example, we also wanted to maximize the total area. Okay? But there are certain problems which you would be interested in minimizing the function. So if you want to minimize your cost, for instance, okay, then that would be a minimization problem. Okay? That would be a problem in which you would try to minimize total cost. Okay? So in this case, we have a maximization problem. And this is the objective function. So as a result, we have 4 ingredients, right? So we have the decision variables, we have the parameters of the problem, we have the constraints, and we have the objective function. Okay, and these are all the sort of ingredients that are required for a mathematical model. So now we're going to construct our first, basically, mathematical model. Now, since this is a maximization problem, okay, we're going to start with the abbreviation MAX. So MAX actually stands for maximize. Okay? If it were a minimization problem, then we would have started with min, M-I-N. Okay? So next, we would like to express our objective function, but we want to do this in terms of our decision variables. So here's a question, basically. If I know the values of x1 and x2, I can actually compute the total revenue, right? Okay? So I need to go back here as well. So for example, if x1 is equal to 10 and x2 is equal to 0, you can actually compute the total revenue, right? So how do you compute the total revenue? Well, if x1 is equal to 10, you multiply 10 by 2.5. And if x2 is 0, then you multiply 0 by 1.5, and you add them up. Okay? Now the question is the following. So how can I express my objective function in terms of x1 and x2? So what's the formula to compute total revenue? Well, it's going to be 2.5 times x1 plus 1.5 times x2, right? And with that formula, if you give me values of x1 and x2, I can compute total revenue immediately. Okay? So as a result, I can write my objective function in the following way. So I want to maximize 2.5 times x1 plus 1.5 times x2. So this is precisely the formula for total revenue, provided that you produce x1 liters of low-fat milk and x2 liters of regular milk. Is that clear? All right. The next line actually reads s.t. What does that mean? That's actually a short form subject to. So this is the expression that we would like to maximize, okay, by playing with values of x1 and x2. Subject to basically means that you cannot choose x1 and x2 arbitrarily. Okay, they have to obey certain restrictions, and that's going to correspond to our constraints. Okay, so what are the restrictions that should be satisfied by x1 and x2? Non-negativity, I'm going to come back to that. Let me start with the available machine time. Okay. Okay, so essentially what I need to do is the following. On machine 1, the total amount of time I can use is 12 hours, right? Okay. Here I have everything in minutes, so I have to first convert it into minutes, right? So how many minutes is 12 hours? 720, right? So just multiply by 60, so as a result you get 720. So total amount of time I'm going to use on machine 1 cannot be more than 720. Okay? So what should I do? Well, I should figure out how much time I use on machine 1 to produce x1 liters of low-fat milk and x2 liters of regular milk. Okay? So how am I going to express that? Well, 3 times x1 plus 2 times x2, that's going to denote the total time on machine 1 that I'm going to need. Right? So let's write that down. So 3x1 plus 2x2. Now what do I know? So that number, that expression cannot be larger than 720. Okay? So what should I write? Exactly. So I should say that this expression should be always less than or equal to 720. Where does 720 come from? Well, 12 hours times 60 minutes is 720 minutes, right? So the left-hand side of the expression is that this is the total amount of time I'm going to use on machine 1, and this is total available time on machine 1. Okay? So total time I'm going to use on machine 1 cannot be more than total available time. And that's quite intuitive, right? So I should do the same thing for machine 2. Okay? So how much time do I need on machine 2 to produce x1 liters of low-fat milk and x2 liters of regular milk? Well, 1 times x1 plus 2 times x2, basically, right? So I can write it as x1 plus 2x2. And what's the available time on machine 2? 6 hours. I need to turn it into minutes again. Okay? So by the same reasoning, this should be less than or equal to 360. Okay? So that actually models the constraint that we cannot exceed the available machine time. Okay? What else do we need? Non-negativity. Never ever forget that. So x1 should be greater than or equal to 0. And x2 should be greater than or equal to 0 as well. Well, this is all we need basically, okay? So this is the mathematical model of this simple production planning problem, okay? So what we want to do is we want to find the best value of x1 and x2. And what do I mean by the best value? The value that maximizes this function, okay? But I can only choose values of x1 and x2 which satisfy all of these restrictions, okay? So if you think about this a little bit, then, you know, these constraints define the set of allowed values for x1 and x2. Okay? So for example, I cannot choose x1 to be 1 million and x2 to be 2 million. Okay? Why not? Because then I would violate these constraints. Okay? I cannot choose x1 to be minus 5. Then I would violate this constraint. Okay? So as a result, one way to sort of view this problem is the following. Among all values of x1 and x2 that satisfy all of these requirements, okay? So this actually defines a set, right? So this defines a set of values that x1 and x2 can take. Among all values in that set, I want to pick the one which will give me the largest value of this expression. Okay? So among all possible production plans that I can come up with, I would like to sort of pick the one that would give me the largest total revenue. Okay? So as a result, this is my objective function. These are my constraints, and x1 and x2 are my decision variables. Okay? If I can solve this problem, and if I can obtain the best values of x1 and x2, then I can take those values and give it to this person and say that, look, x1 corresponds to the number of liters of low-fat milk, and you should produce, let's say, 50 liters of low-fat milk. And if x2 is equal to 100, you should produce 100 liters of regular milk. Okay? So as I said, this is our first model in this course. Well, first real model, so to speak. Okay? The area problem was a model as well, but this is the first mathematical model. And in the first part of this course, as I said, we're going to actually start constructing such type of models. Okay? So this is a very simple problem. Starting with the next class, we're going to start looking at more complicated problems. Okay? And what we're going to do is we're going to sort of take that problem and turn it into a mathematical model by defining decision variables, by looking at parameters, by looking at constraints, and by defining the objective function. And once we have all these four ingredients, then we can actually write such a model for the corresponding problem. Okay? Any questions? All right, so well, let me stop here. So unless there are any questions. All right, so I'll see you on Thursday at 9:40, okay?